We discussed in the previous class about the turbojet, turboprop and the turbofan. Now let us look at the next engine that got developed, that is the ramjet. But before I go there, I just wanted to ask you something. Suppose I do not add heat, I do not have the combustion chamber in a turbojet engine, what happens then? Will it produce thrust? Why?
We need some external power to run the compressor, because without, in starting if you run the compressor,
compressor is run,
external work,
compressor is run, then you have the turbine.
What I have extracted from the fluid in the compressor will be balanced, put into the fluid in compressor.
Yes.
Will be what I extract in the Adme. Already there is efficiency. There is nothing to be.
True, correct. So you are saying that if I do not have the heat addition, then it is impossible to produce any meaningful thrust. Okay. Now the concept of a ramjet, it's evolved from a turbojet. The idea here is, let us say I am flying at a very high Mach number of around 2.5. Okay, fine. So let us do that calculation. If I have a flight Mach number of around 2.25, okay, then what is the stagnation pressure that you get? P naught by P. This ratio is goes as 1 plus gamma minus 1 by 2 m square. This you will, if you do this calculation, you will find is around 11.2, right. If you remember when we discussed about the turbojet and when we were talking about efficiencies, we talked about diffuser efficiency, right, and we said diffuser efficiency is somewhere around 60 to 90% and it depends on the flight Mach number. So even if you assume something like 60 to 70% efficiency, of diffuser, yeah, huh? Sorry. So if you assume efficiency of the diffuser to be around 60 to 70%, this number works out to be around the actual pressure recovery from this stream works out to be something like around 7. Now you have a fluid that is already compressed, okay, to something like 7 times the ambient pressure. So I do not need a compressor. So if I do not need a compressor, I do not need a turbine, and so you do not have any moving parts, and that is the essential idea of a ramjet. So if you see this figure here, this is a typical schematic diagram of a ramjet engine. What you have here is a supersonic diffuser, and then you have, at this point the pressure of the incoming flow is already higher compared to the ambient pressure, okay, and then you have fuel injection here and the fuel flame holder here, and the combustion takes place, and then you have the flow expanding through the nozzle, okay. So you do not have any turbine, you do not have any compressor. So, a ramjet has no moving parts. Okay. And in that sense it is very simple to design. It operates very efficiently. Between a Mach number range of 2 to 4 okay. Now what do you think if you compare a ramjet with a turbojet, what do you think would be the thrust to weight ratio of this compared to a turbojet? You think would be higher, lower? It will be higher. So, the thrust to weight is higher, thrust to weight would be something like 160 to 170 Newton per kg for a ramjet, and for a turbojet this is for a ramjet. Okay. Now, if you have a turbojet, the thrust to weight ratio would be something like 40 to 70 Newton per kg, and for a turbo fan it would be lower than the turbojet. So, okay. So, the thrust to weight of a ramjet engine is the highest because it has no compressor, it has no turbine, there are very few parts. So, it can be very light. Okay. What about SFC? What do you think would be the SFC of a ramjet compared to a turbojet? Would it be higher, lower, or same as turbojet? Huh? Think it is going to be the same? Actually, if you look at a ramjet engine that you have here, this ramjet engine is very similar to what you have an afterburner in a turbojet engine, right. What happens to the SFC in the afterburner? Is it higher or lower than the main engine? Lower, higher, right. In a turbojet engine, the SFC of with the afterburner on is higher than the SFC with the without the afterburner on. So, a ramjet engine is very similar to the afterburner of a turbojet engine. Okay. And therefore, you will find the SFCs are much higher. So, if you compare SFCs for ramjet you will find ramjet SFCs to be 60 to 90 milligrams per second. This was around 31 to 36 milligrams per Newton second and 16 to 24 milligrams per Newton second. So, you see that in the ramjet the SFCs are much higher. The main reason for this is you are adding heat in a ramjet at a much lower pressure than what you do in a turbojet main engine with the with only the main engine, that is without the turbo afterburner on. If you are adding heat in the main engine, then you are adding heat at a very high pressure. So, therefore, the availability is more. So, you can extract more work out of it. Remember, we are always going to expand only for pressure, we can expand only for pressure. Okay. So, if you add heat at a very high pressure, you can extract more work out of it. So, the availability is more. So, in a turbojet engine you are adding heat at a much higher pressure compared to a ramjet engine. Therefore, you will find the SFC of a turbojet engine being lower than that of a ramjet engine. Okay. And one thing about the ramjet engine is that somehow you should go to a high Mach number, right. So, if you do not go to a high Mach number, or if you do not go beyond the speed of sound beyond Mach 1, then the compression will not be large. So, you need, it cannot be a self starting system. So, you need something to take it to from 0 to 2 Mach number or something like that, from where it can carry on further. Okay. Otherwise, it is not a self starting system. That is one of the drawbacks, and usually rocket motors are used to take it from 0 to the design Mach number, and then these things operate at that particular Mach number. Okay. Now, what are the applications? What are the applications of ramjet? These are typically used in missiles. Okay. So, and in the Indian scenario, you have Akash and BrahMos that are ramjets. Okay. There is also an aircraft, a very famous aircraft that used a ramjet, SR-71. Yes, SR-71 was a unique design. It is a turbojet and a ramjet put together. Okay. That is the only aircraft that did that, and it had a very high. Yes. So, it had a very high Mach number because it used that ramjet. Okay. It could bypass and operate in different Mach number regimes differently. At high Mach numbers, it was operating as a ramjet, at lower Mach numbers differently. Okay. So, SR-71 was the only aircraft that has used this, otherwise it is primarily used in only missiles. And if you look at this, I have put together some data here, wherein you see for different missiles, okay, the diameter and the weight and the thrust and the maximum speed it can go to. Okay. Some of them are ramjets, plain ramjets, and the others are integral ram rockets. We will talk about what integral ram rockets are a little later in the course. The first and the last ones are ramjets, okay, and the others are other two are integral ram rockets. Okay, fine. Now, in a sense, from the piston engine plus propeller, which was flying at very low speeds, we have come from piston engine plus propeller to a ramjet, which can take us to something like Mach 4, right. Why not beyond it? What is the trouble beyond it? Why can't we go beyond Mach 4 with a ramjet? Huh? Sorry? Drag. Okay. Any other?
Ramjet work on a principle like putting the air onto near to stagnant condition. So if the Mach number is higher, the stagnation temperature will be much higher, and then
okay, yeah. Ramjet stands for supersonic ramjet. Okay. Now, if you take a look at a ramjet wherein the flow Mach number, as you rightly said, is brought down from ambient condition to low subsonic inside the combustion chamber. If you take a look at that,
supersonic combustion
sorry, thank you. Okay. Now, if we were to do the calculation of what is the temperature at the end of this compression process, okay, for different Mach numbers or the entry Mach numbers, I will put that as m infinity, and if we were to calculate T stagnation, we will find that at a Mach number of 4, the stagnation temperature is somewhere around 980 Kelvin, and around 6 goes to 1788 Kelvin, and 7 it goes to 3300 Kelvin. Now, the trouble is, if you are using kerosene as the fuel, okay, if we remember our previous discussions, the adiabatic flame temperature that you can get with kerosene air combination is somewhere around 2300 Kelvin. Now, if you look at this table, you have T stagnation itself going to something like 2260 at a Mach number of 7. So, what it tells you is beyond this point it will be very difficult to add any sensible heat to the flow by burning a fuel, right, which is why I asked you the earlier question. Suppose I do not add heat, what will happen, right? You will not get any thrust even here. So, you need to add heat, and to be able to add heat you need to ensure that the temperatures do not go to such high values, okay. And what you do in a ramjet combustion is you bring down the velocities to nearly subsonic conditions at the entry of the combustion chamber. Now, the idea is if you do not do that, if you let the flow velocities be supersonic even at the entry of the combustion chamber, then the temperatures will not be so large, and therefore you will be able to add heat, okay, and that is the idea of a supersonic ramjet. So, let us say you have a flight Mach number of around 8, then in the combustion chamber if you can allow a Mach number of around 2.7, okay, then the temperature of flow at the entry point of the combustion chamber will be something like 1200 Kelvin. Now, surely this is a harsh temperature, but it is still not very large. So, there is scope for adding some more sensible heat by burning a fuel, and then you can expand the flow through a nozzle. There is also another problem that I did not talk about here, that is once you go to such high temperatures, the oxygen and the nitrogen in air, they start to react, okay, and the oxygen content in the air slowly begins to deplete. You will not have the same amount of oxygen content if you bring the flow from somewhere around Mach number 7 to around stagnation conditions. So, if you take a look at those numbers of the oxygen in the air, it ranges from something like 0.21 So, the oxygen content you see is decreasing, okay. So, because of these two problems we have looked at what is known as a scramjet. Now, scramjet, it is easier said. Let us say we can bring down the Mach number from 8 to 2.7 and then do the combustion at 2.7 Mach number. It is very easy to say this, but very difficult to do this. The idea of a scramjet has been there for a very long time, more than 30 years now, and yet no country has ever flown anything with a scramjet. The Americans have recently tested something, the Australians have recently tested something, the Japanese have a program, Indians have a program, but Indians have only tested it without fuel addition. ISRO has tested it very recently without any fuel addition, only aerodynamic testing. The Americans have tested it with the fuel addition, and they claim to have produced positive thrust. We will see why is it that it has taken us this long from the concept to realization stage. What are all the difficulties involved with scramjet? Why is it taking us this long from concept to realization? The first problem is, if you look at this Mach number here, you are not bringing down to stagnation conditions. So, therefore, the static pressure in the combustion chamber will be low, right. Because of this, now reaction rate between fuel and oxidizer depends on this static pressure. It goes as reaction rates goes as square of the pressure typically. Now, if the static pressure is lower, then the reaction rates will not be faster. The reaction between fuel and oxidizer is not happening at a much rapid rate that you want it to be. Okay. So, reaction rates are very low. Now, there is an additional problem. You are saying let us somehow bring this Mach number to something like 2.7. Typically, in gas turbine engines as well as in ramjet engines, this Mach number would be 0.3, right. From 0.3 to nearly 10 times that is the Mach number that you are looking at. So, the flow speeds is very large through the combustion chamber. Okay. Flow speeds are large means what? If you have a particular length of the combustion chamber, then the residence time of the reactants is very small. So, this is like a double whammy. Firstly, you have reaction rate slower, and on top of it you are saying residence time is going to be small. So, it is like a no win situation that we are getting into, right. So, that is part of the reason why it has been so difficult for realizing this. The other part is, if you look at the typical gas turbine engines that we use for aircrafts, Boeing makes the airframe, right. Boeing or Airbus makes the airframe, and Pratt and Whitney or GE makes the engines. So, expertise of engine making and airframe making are not in the same place, they can be distributed. You can make the aircraft and then match the power and fit this engine and go about it with regards to any other aircraft. We are making the airframe for the LCA, we are using a GE engine right now to power it, right. So, airframe development can take place separately and the engine development can take place separately. This is because there is no great aerodynamic coupling that is there between the two of them. Okay. The aerodynamic coupling between the structure and the engine is not too large in most systems, but in this case there is a very strong coupling between the airframe as well as the engine. So, you can't develop them separately, you have to do them together, okay, and that is one of the major drawbacks. Interaction between engine and airframe is very high in the case of scramjets. So, you can't have expertise in different places, you have to have them together, which is not always easy, okay. And even testing, you cannot if you are looking at any of the turbojet or turboprop engines, the engines are developed separately, they are tested somewhere else and then they are fitted here. All the testing and other things will have to be done on the airframe and the engine being integrated together if you are looking at a scramjet, and that is not always easy, okay. The other major problem here is drag. If you look at the drag, both the pressure drag as well as the viscous drag is high here. Because you are going at very high Mach numbers, the drag is very high. Now, you want inside the engine a Mach number of 2.7, right. If you are wanting that and if you want to ensure a reasonable residence time, then the length of the vehicle will have to be long, which means that the drag will also be long, I mean will also be large, okay. So, drag in this case is very large. So, in most engine tests, flight tests, unless people come up with realistic numbers, as in they put out these numbers, it is very difficult to believe whether the system produced any positive thrust or not, okay. Please also remember that even on the inside there is a viscous drag, because the flow Mach numbers inside the engine is also very large, and typically the engine length is comparable to the entire vehicle length in this case. So, the drag is a serious problem here, very large drag. And lastly, testing of this is very difficult, because you need to test for the engine as well as the structure, right. So, and if you are to build a wind tunnel for testing this, it is very expensive, because as you go to higher and higher Mach numbers, the power required to keep it running for a small time is very large, okay. So, testing is a problem. You can test only small scale, right. But the other problem is how good is your scalability, that is, if you test something at small scale, can you go ahead and use it at a larger scale and be confident that whatever you have done at a smaller scale is going to be valid. It is not going to be easy if you have a circular intake. So, which is why people go in for a rectangular intake, because you can add them up. If you have one rectangular intake and do the testing on that and do everything, then you can make a large engine by simply adding up all these rectangular intakes. So, that is one way in which people have looked to address this problem. Okay. So, you can have a rectangular cross section, so that you have modularity of design. Okay. Why then are we interested in this? We simply seem to be putting too much of problems here. We are only stating problems, and the way it has been stated makes one feel that there is no hope. It is also true that people say it is not very easy, people in the field who are doing this, not very easy probably to get an accelerating system in a ramjet, a scramjet. Probably possible if you take it to that kind of Mach number, somehow it can probably sustain itself, that is, it can just overcome the drag. Okay. Why do you think people are looking at this? What is the motivation for just flying faster is not sufficient, no? The kind of money that is being invested in this kind of activity is very, very large. There must be some other reason why people are doing this.
Outer orbit.
Can't go beyond atmosphere with this. No? Okay. If you look, there are two applications always, or in this case 3 applications. If you look at a launch vehicle application, because in India both ISRO and DRDO are pursuing a separate program, okay, and there must be a reason why they are pursuing it. If you look at a launch vehicle reason, as in if you are using this to launch something into orbit, typically currently launch vehicles use rockets to do this. Now, we will come to what rockets are a little later in the course, but just for this argument, rockets have to carry their own fuel and oxidizer on board, which means that their weight of the system goes up, right. As compared to that, if you look at any of these air breathing engines, they will use the atmospheric oxygen, which is usually a few times larger than the fuel that is required, right. So, they end up using atmospheric oxygen and use carry fuel on board. Now, with a ramjet we have a limitation of around Mach 4, right, that is the limit at which we can go up to right now. But if you go for this, you can go to a larger Mach number inside the atmosphere, and therefore, if you can develop this successfully, the costs of launching any satellite would be much smaller if you have a large portion of it being air breathing. Okay. That is the idea why ISRO is pursuing it, fine. Now, if you look at a military application, why do you think a military would be interested in this? If you have a missile that is built around a scramjet, and if it can go at Mach 8, it is very, very difficult to track it and shoot it down. Okay. You might argue that we already have ballistic missiles, why the hell do we want all these different kind of things? They also go at very high Mach numbers, but there is a difference. If you look at what a ballistic missile does, it is powered only for a part of their flight, the remaining part it is going as a stone. It can maneuver itself depending on the aerodynamics, but it is not powered during the entire flight period. Okay. It is only powered during a portion of the flight period. But if you have this, it is powered through the entire period it is flying, and therefore your maneuverability is very high. Not only are your speeds high, your maneuverability is also high. So therefore it makes it very difficult for the enemy to shoot it down, and that is the reason why military is going ahead for this. And if you look at any civilian application, typically current day technology that we have, the San Francisco to Tokyo flight takes something like 14 hours. Okay. People say that if you have a Ramjet engine, then you can do this within 2 hours. Wouldn't it be nice if you can fly between any two places that far within just 2 hours? So that is the motivation behind looking at this from a civilian perspective. Although the civilian perspective is very far away right now, people are looking at only the military and the launch vehicle application. Most innovations that we have will always go through this, especially related to aircrafts and aerospace industry, will always go through this cycle. Firstly, it will be the military that will put it to use or develop the technology for its use, then the civilian application comes in, right. It has been like this for all the engines. If you look at turbojet engines were invented for a military purpose, right, and slowly it got changed and morphed, and then you have this civilian application that is coming in, right. So any kind of engine development or any kind of such activity, firstly it will be the military application, and then you will have the civilian application. Okay. I think I will stop here and continue in the next class.